Okay, I would like to thank the organizers for inviting me to speak here. I'll be talking about the semi-infinite Hodge structures. And some of you guys might have seen this talk before, so I apologize for that. This semi-infinite Hodge structure has its origin from Qt-Cyto's study of higher residues and primitive form in this period map for isolated singularities. So this is generalized and systematically developed in Calabi-Yau geometry by Barnikov-Kontsevich. So basically, this stuff is about to study the Hodge theory aspect of the following data. So suppose you have an holomorphic function, and you try to study the Hodge theoretical aspect of this map. And that's essentially organized into this structure. So I'll be explaining this structure in two different perspectives. One is from this topological string, BTS topological string. The other one is from like a CyberWitten geometry that is realized by singularity theory. And so this is the outline. I would like to motivate this semi-infinite Hodge structure from Qt-Cyto's original version. So let me start with this drum theory. Everybody is familiar with the drum theory. And suppose X is a compact-oriented M-manifold. Usually, the drum theory will do integrations, and you integrate this kind of differential form to get a number. And here, like you pick up like top form, and get a number to do integrations. But you can like model this integration by studying this algebraic model for this like a drum complex. So for example, this integration map is the same thing as sending a top differential form to its top drum cohomology, which is one-dimensional. So basically, if you know this algebraic drum complex, this algebraic model, you know this integration. That's another way of saying this. Then this kind of this semi-infinite Hodge structure basically can be viewed as an algebraic model for understanding this complex oscillating integral. That's the analog of this two story for understanding integration. So let me explain some basic notions from this original example. Suppose f is an isolated singularity, it's a holomorphic function with isolated critical point at the origin. And usually we consider this quotient, so this top form divided by df wedge n form, omega x n. Then somehow if you choose a holomorphic volume form, for example, this trivial one, you can identify the space with, for example, this Milnor ring, this Jacobian ring of this polynomial or this function. And somehow this captures a lot of information, deformation, and so on. And in particular, there is a non-degenerate pairing on this space, which is given by residue. So this is residue pairing plays a role of Poincare duality. Now, what's more interesting is the following. Like, now this guy is the leading part of the so-called Briscoe lattice. This is a very deep notion in singularity theory. So roughly speaking, the definition here is about following. Like, this is like a -1 form quotient by df wedge exact n forms. So I would like to compare with the original one that people usually are familiar with is about this Jacobian rings. This mod out this order of these n forms. Now you want to mod out this kind of exact n forms. Now on this space, there's a lot of structures. As I said, like this structure somehow models this complex oscillating integral. So for example, and here's an operator, let's call this operator T, acts on this space. So given an element here, so this is represented by a top form, and we work locally as a germ. So we know by Poincare lemma, there exists an n form beta such that alpha equals d beta. Then we define this T operation by applying alpha to get this beta wedge minus df. And symbolically, I mean, you can visualize this map, this operator, as defined in this way, sending up to d inverse and wedge df. And it's an interesting exercise to check that this is well defined on the space, and that's a very essential operation. Then, with this operation, you can define the following structure. Starting with this guy, we define its case descendant form by applying this operation k times. I can do it like infinitely many times. I mean, from this data, this gives a natural so-called semi-infinite filtration. So this original Briscoe lattice, you apply once, twice, and so on. You get an infinite filtration. And if you take a formal completion of this guy with respect to this kind of t-adic topology, you identify this guy with something more familiar. I mean, it's like a twisted around complex. So this guy, I mean, this is a formal power series, and with this differential, somehow this can be viewed as modeling this kind of like a perturbative theory, and this why it's analytic, non-perturbative. Now, on this Briscoe lattice, the surprising structure is the following. Like, you decide to construct the so-called higher residual parent on this Briscoe lattice. So you evaluate it on this kind of formal power series ring. And this leading term, if you, I mean, we see like this definition, somehow you can see leading term is exactly the stuff we discussed before for the residues. So this higher residual parent, the leading part of the higher residual parent is precisely the residual parent, which satisfies this Poincare duality property. Then somehow you can extend this parent to this kind of a Lorentz series, and to get this kind of a bigger one. I mean, that's for convenience. So this guy is the essential, most important object in this talk. Now here, let me give it a formal definition. I mean, this is a little bit long, but this is motivated from this what we have seen before. So a semi-infinite Hodge structure of 8n consists of the following data. So this guy is a 5-dimensional vector space over this kind of a formal Lorentz series. So you can view this one as a vector bundle on the puncture disk. And this guy is a lattice. And then there's a meromorphic connection with irregular singularity at the origin. So this irregular singularity basically captures all of this kind of Lefty symbols and so on, status phenomenon. Then, I mean, there's a compatible connections. This is like along this direction, somehow such that which is compatible with the higher residual parent. And we know the leading term is nothing but it's a usual residual parent. And this data forms is kind of like and semi-infinite Hodge structure. This is an example from singularity theory. And again, if you deform this singularity, this guy also varies in an interesting way. So, like the usual variation Hodge structure. And I would like to explain how to use this structure to do really something essential. So the first thing is about this kind of oscillating integral. I mean, given the element of this Briscoe lattice, we can consider the following this integration over this kind of like a Lefty symbol. And like usually under Laplace transform, this information the same thing as understanding this period map on these vanishing cycles. Now I would like to comment on some analog with the CyberWitten curve case. I mean, this will appear later again. So in CyberWitten curve geometry, we have two forms, like say omega. We usually write it like a d lambda, then look at the period for lambda. So this process can be organized in the following way. Like if you would like to understand this period of this lambda over vanishing cycles, this lambda same thing as this operation, the inverse wedge df divided by df. And as I mentioned, like this operation, the same thing as the first descendant of the form. And this is the way you obtain this Seiberg-Witten differential. But if you go to some other dimensions, you will see like something similar happened. But you have to pick up the different descendants. I mean, this is a curve case, but if you go to some other dimensions, some other geometries, you pick up the different descendants. And that's, I will explain this later. Now, this algebraic model, like, what's important is the following. Like, if you look at, for example, the deformation space of this polynomial or this holomorph function, and usually represented by some kind of so-called universal unfolding, and the lambda is the coupling, is a deformation parameter. And using this semi-infinite Hodge structure, Q Saito, I mean, around early 1980s, constructed a special family of holomorphic volume forms. And this is highly non-trivial, actually, the weight. And it's called primitive form. And its construction is rather involved and fully used the semi-infinite Hodge structure, but somehow it determines a set of flat coordinates satisfying this kind of quantum differential equations. And this is nowadays is like becomes a equal coupling for these 2D lambda give B models. And originally, I mean, this is like this construction is purely somehow algebraic and analytic. I mean, using this purely from the semi-infinite structure. Then on Calabi-Yau geometry, the analog of this primitive form is called a semi-infinite period map. And in the context of commutation theory, this is related to given Telstra function, and that's That's how it appears in the literature. Now, I would like to explain this structure in this kind of topological string, in particular B model. And so it's, this kind of stuff is set up on this on Calabi-Yau. So I'm going to start with the Calabi-Yau. As a Calabi-Yau manifold, this is a Calabi-Yau volume form. And around like 1994, like Brzezinski, Sokori, Ogrivafa, they proposed that this B-twisted topological string field theory on this Calabi-Yau threefold is described by this Kodawa-Spencer gravity. And this is basically, if you look at the equations of motions, describe deformations of Ricci-Flat metric in terms of these complex structures. And somehow, a couple of years later, before, like with Kevin Costello, we find an extension of this Kodawa-Spencer gravity, somehow in the sense of a Seiberg-Witten. I'll explain this later. And it's formulated on arbitrary Calabi-Yau. We're going to call this one BCOV theory. And this guy is somehow interesting. I mean, this is also fully use of the structure of semi-infinite hodge data. And this can be coupled with holomorphic Simons in a cyclic version of conservative formality. I will try to explain this as well. And that's roughly the data. So let me try to explain the geometric and the physical meaning of this kind of a BCOV theory we proposed. So I'd like to understand the deformation problem of a Calabi-Yau structure. So you want to deform a Calabi-Yau means like you want to deform this pair, x and omega x. The deformation of the pair can be specified by two data. One is like a 0-1 form valued in this holomorphic tangent vector. The other one is a smooth function. But this mu is the usual one, like satisfying this Mori-Karan equation. That's the deformation of complex structures. And this function basically is specified as a deformation of the Calabi-Yau volume form. And these two equations describe the pair deformation. But there's a nice way to look at this equation. I mean, you can package this stuff into a single equation. So here, the mu tilde is a combination of this mu with the rho. That's the complex structure in the volume form. And you can also cook up this operator, which is with the deformation of the bar operator. And the del operator is a divergence operator, like with respect to this Calabi-Yau volume form. And this single equation describes these two equations. So you see, like to describe Calabi-Yau geometry, I mean, this is the essential equation. Now, here, this is like our definition for the fields of BCOV theory. And I hope motivated a little bit the definition from the Calabi-Yau deformation theory. So this is like a polyvector fields with a formal variable t. So this is like all smooth polyvector fields, like anti-holomorphic forms valued in these exterior algebras of holomorphic tangent vectors. And t is a formal variable, and this is with a differential in a bracket. It's like a Skelton analysis bracket. And this is an interesting DJOA. And somehow this Mori-Karan equation describes the extended deformation of Calabi-Yau structure. So this is somehow describe the correct equation motion. And also on the space, there's an analog of a higher residual parent I just mentioned. I mean, this is the integrations of polyvectors using this volume form and some kind of combinations of the like a variable t. Now this is our definition for the fields. Now the problem is the following: like once we have this equation motion, we describe the correct data. And first, as a comparison, like with the original version, like this can be viewed as a resolution of BCOV's Kodawa-Spencer gravity. So in that theory, I mean the fields are given by this kind of divergence-free polyvectors. And now the problem is like we want to write down some kind of generate this kind of Kodawa-Spencer gravity, and for this particular topological string field. Now we want to write down some action functional that we can do help us to do quantizations. And somehow we tried very hard to find like seems like we cannot write down a single action with this kind of equation motion. And this gives a big trouble for a long time. But later, I mean, we find something interesting. Like we try to do some kind of like transformations within the category of differential gradient Lie algebras, and we fail. But actually, if you do something like if you enhance it, I mean, in the category of like L-infinity algebras, it turns out like we can perform an interesting, highly nonlinear L-infinity transformation of this equation to get something that we can write down action functionals, and that's actually an interesting part. We're going to call this one BCOV interaction. So I will try to explain a little bit about how this stuff appeared. And this nonlinear transformation is precisely the data of the period map arising from this kind of semi-infinite Hodge structure. Let me try to explain how this appeared. But first of all, I mean, to explain this nonlinear transformation, so first I would like to explain the setup for these semi-infinite structures. So here you have the polyvector fields. Now you look at a bigger one, like previously the fields is given by this kind of a formal power series in T, but now you enlarge it to this kind of a Lorentz series. And on this bigger one, you can construct a symplectic space, a symplectic pairing. Basically, this part is the higher residue, and basically you take the residue in T again. So you see like this symplectic pairing pairs like the non-negative orders in T with the negative orders in T. So this is actually a very standard pairing on this loop space. Then for this symplectic space, it considers the following guy. This is like a period map. Basically, this period map is mapped from this space. This is our original field space to this symplectic space. And this is the formula by standing a mu to this guy. The meaning of this formula is like, somehow you can see like this term represents the deformation of Calabi-Yau volume form. So this map is nothing but a cochrane level of this periods of the corresponding Calabi-Yau. So this is basically this period map. And let's visualize this map as something like this. It's highly nonlinear anyway. So you're going to see what's the effect of this map. And somehow, first thing you observe is the following, like this period map embeds our field into a Lagrangian submanifold of this symplectic space. This means that if you formally identify this one as the cotangent bundle of this is like a Lorentz series, this is like a formal power series, as a cotangent bundle of this guy, and because it's a Lagrangian, you can write down the generating functions. So let I0 to be the generating functions on this guy for the subimage of this period map. So you know the existence by the usual symplectic technique. Now, and you can compute it. If you compute it, you find something interesting. The action functional is local and is given by the following form. I say integrations of this type, and this type is nothing but intersection theory on this in pure gravity. I mean, this is like on the modular space of a rational curve with Mach points. So, for example, if you look at this combination, order n part, this coefficient, by picking up these orders in T with this coefficient, that's the psi-class intersection on M0n. And then for the other part, polyvector fields, you take the wedge and integrate. And moreover, like this guy, this action functional, I mean, satisfy a version of a classical B-wave master equation. But this B-wave structure is degenerate. Basically, you have this Poisson, the B-wave bracket is -1 shifted degenerate, not the symplectic. And this causes a lot of trouble, by the way. But this one satisfies this kind of DG version of a classical mass equation. And if you look at a leading term, like a leading term is a QP interaction part. That's precisely the Kodawa-Spencer gravity studied by BCOV. And so this is like how this Kodawa-Spencer gravity is extended, I mean, and to the full solution of classical mass equation. And actually, there's an algebraic model by Angelosov I would like to mention about this construction as well. Now here's the transformation that I mentioned. So originally you have this equation of motion, which is hard to write down kind of action functionals. But then you perform this period map. So this period map is the following, like you map this one to this guy, this is the equation. Now we want to identify this one as a graph, this graph of the generating function. So we project this one down to this line to get it back. So this operation is like pick up the non-negative orders in T. And you can expand it. I mean, this is like a very complicated. So that's why it's a highly nonlinear transformation. This is actually an L infinite transformation. And now later, if you push, I mean, this equation under this map becomes the critical locus of this guy with a DG version. And that's how this kind of theory works. And now start with a solution of classical mass equation, like the standard way to quantize, I mean, in the BV stuff. But this case is like a degenerate BV, but it can still do the same thing, like solving this kind of a quantum BV mass equation. And we have the standard UV problem, like this is divergent. I mean, we need to regularize the stuff and so on. I mean, for example, at the local level, this is not well defined, and this kind of a standard problem. And we want to get this done like rigorously. And then there are many ways of doing this. I mean, just to expand this kind of like quantum mass equation. And so I used a way that is developed by Kevin Costello. I mean, I call this one homotopic renormalization. So it basically study from this unrenormalized point. You go to some kind of regularizations, preserving BV structure up to homotopy. And you can solve these homotopic BV structures nearby and related to each other by this kind of version of homotopic RG flow. And you can set it up, I mean, the whole theory by the mathematical meaning of this quantum mass equation. And that's roughly the quantization. And after you solve this quantum mass equation, and you can get a generating functions on the zero modes. This is called modge. Now, you want to compare this one with the calculations in Gromytin theory, for example, in the mirror symmetry. And this co-modge, you want to identify this one with the co-modge like of this polyvector fields. That's the usual observables in this kind of B model. And then this requires a choice of splitting of the Hodge structure. So actually, I was talking about the semi-infinite Hodge structure, but the splitting requires the other half. So somehow, if you do this, if you identify this one, if you collect all these kind of like Feynman diagrams, you find the invariants, the generating functions on this kind of zero modes. Actually, if you can do a very explicit calculation. I mean, for example, like simplest example is like a elliptic curve. Actually, from this data, you recover the full, like the descendant Gromytin invariance on the elliptic curve. And here I would like to mention that splitting is a choice. If you choose different splitting, this number you get is different. And this dependence is precisely the holomorphic normal equation. So geometric interpretation of this kind of quantum mass equation is that it defines a Q-closed element eventually in this Fock representation of the Y algebra that quantizes the digit sympathic space. And this digit sympathic space arises from this kind of semi-infinite Hodge structure. And that's how this one appeared in this kind of topological string field theory. Now, I probably would like to skip this part, I mean, for integrable hierarchy, but in case people will ask later or be interested in, I'll come back. I would like to explain this, open string part. I was describing this kind of like closed string part of this kind of B-twist topological string, but now you can also couple this one with open string, and it turns out this coupling is highly non-trivial. So this kind can be coupled with, for example, this open string field theory in the B model. Is described by Witten's holomorphic Chen-Simons theory, and it's kind of action functional. And somehow we want to couple in a way that satisfies Seiberg's open-closed BV mass equation. And how to put this one together? If you naively add them up, it doesn't work. I mean, there are a lot of terms missing if you require this kind of gauge symmetries and so on. And here's the hint. And this is a hint by understanding the large property of this holomorphic Chen-Simons. So the first calculation I did is the following. Now we don't basically this closed string give you a deformation, so we try to understand this problem using deformation theory. So you start with the holomorphic Chen-Simons in the Lie algebra like GLN. You want to deform this holomorphic Chen-Simons, like preserving gauge symmetries, and in a way in the large n limit. If you compute this deformation, it's computed by some kind of Lie algebra cohomology. And this first order deformation is precisely by single trace operators. It's precisely parameterized by this space, polyvector fields with a formal variable t. So this is basically the Kolyva-Spencer gravity. So this appeared as a first order deformation. The way to prove this theorem is basically a version of like a secant-Laudet equivalent theorem on computing, relating this like a Lie algebra cohomology on the large n limit and the cyclic homology. And also somehow the classical limit is like Hochschild-Kosten-Rosenberg isomorphism. So I give you first of example, like if you turn on some kind of a polyvector fields without descendants, they give you the following deformation of this holomorphic assignment. So this is like a polyvectors. You have a bunch of differential operators applied to this kind of connections and multiply them together. That's the first order deformation. But if you can go to a second order and so on, I mean, many other stuff, and you can package in a very similar way. So here's the full solution. And we propose the classical open-closed bimodal interaction by the following data. So this action functional is a little bit complicated, but it involves the following structure. So here, the field is given by mu is the class transfer gravity. A is given by this kind of holomorphic assignment, the connections. And so the first part, I mean, the CMN is the configuration space of the disk with m points on the boundary and m points on the interior. And so this, to write down this Lagrangian density, first you do integration on this configuration space by some combinations, like for example, what it look like. So if you insert like a bunch of mu's and a bunch of a's, a mu involves basically a bunch of polyvectors. And then it can be viewed as some kind of differential operators applied to either a connection part or this polyvector field part. And this is a precisely conservative graph formula in his solution of deformation coordination problem. And so if you collect all of the possible configurations, integrate, you get something like differential forms, and eventually that's the Lagrangian density, or integrate over x. And this action functional is basically the full action functional at the disk level. For example, this action functional satisfies the classical mass equation of this type, like this is a disk amplitude, and you take a Q operator. It comes with like this BV bracket in the open string sector and the closed string sector. And somehow this classical mass equation, mathematically, this is essentially equivalent to conservative formality theorem, but it's a cyclic version. And yeah, basically that's how you need to collect all of these configurations. Then from this classical, you can quantize it. You can basically show we did an initial calculation on the local version, so you can show like starting from this classical mass equation. By understanding deformation theory, you can construct a canonical quantization up to all topology, like genus with boundaries and so on, in the large N limit. And this is a proof using deformation theory. And that's roughly the data.
What do you mean by this consistent?
No, I mean just mean it's the action function of suppose this. So this is form of the action function is independent of choice of n. So, for example, if you embed this Lie algebra into GL n plus 1, the way you evaluate at n and at n plus 1 is the same. So that's a stable limit in some sense. I can explain more details later, but that's roughly the idea. The larger limit. Now I would like to explain this one in a different perspective. I mean, this arises from understanding some kind of CyberWitten geometry arising from singularity theory. Again, this kind of semi-infinite structure plays an essential role, and I would like to explain this one from this example. So we are interested in this kind of 4D equals 2 superconformal field theory. And somehow we'd like to understand, for example, this low energy effective theory on the Coulomb branch. And usually it's described by CyberWitten curve fibered over the modular space. And lambda is the parameter. Probably have a lot of data like coupling constant, mass, expected values for these Coulomb branch operators, and so on. And then we have these period maps for these one forms over the Riemann surface, and it deforms and determines the low energy photon coupling. That's the general structure. But somehow, like how this is related to the stuff I was explaining, like about the semi-infinite Hodge structure. This is like a construction from physics. Like if you consider type 2B string on this following background, R3,1 cross X, and X is like a threefold weighted homogeneous isolated singularity. And somehow, it is argued to define 4D equals 2 superconformal field theory in the early work of Shapiro Alpha. and also later systematically studied by my collaborator Dan Xi and Yao. Somehow, around the singularity, you find something interesting, like a CyberWitten solution is associated to a threefold vibration. This is basically the defining equation for this X. And sometimes, this is reduced to curve case, sometimes not. So you might have some general CyberWitten solution for this threefold vibration. Sometimes this threefold vibration cannot be reduced, this solution cannot be reduced to curve case. Our goal here is to figure out the corresponding CyberWitten differential for this geometry. Let's set up some basic notions. And let's consider an isolated homogeneous threefold singularity. So it's like with 4 variables. This is homogeneous in the following sense. Like if you rescale these variables, the function rescales. And this is the weight of this rescaling. And this rational number basically is the central charge for the 2D and 2,2 super-conformal field theory, defined by the Lambda-Gibbs model with a superpotential F. And it is argued that to define this 4D super-conformal, we require this stability condition, like this kind of data. Now, if you study the deformation theory for this polynomial, you find some interesting structure. And this kind of Coulomb branch for this n equals 2 theory, somehow locally the local moduli is parameterized by this universal deformation of the polynomial. And here lambda phi alpha is the basis of the Jacobian algebra. So this one basically represents universal deformation. Now, do you want to define some weights? This is a weight from some kind of U1 charge. Then this kind of like so the Q is a homogeneous weight for the polynomial. And roughly speaking, this weight subdivide these deformations into a bunch of data. So for example, this weight less than 1 represents this part, coupling constant part, and also the mass part in the middle, and the Coulomb branch operators. And there's a perfect match between these two, and that's expected. And if you look at the deformations, this is like usually if you compute this homogeneous weight, like this weight goes from 0 to the central charge, and in the middle is 1/2 of the central charge. Now, given this family of this holomorphic volume form, we consider the following period map. So this is like a deformation parameterized by, say, lambda. And suppose you have some choice of the volume form. And you look at the periods of the vanishing cycle. So as I mentioned, like this is over this choice of this deformation, and integrate it over some kind of choice of vanishing cycle, and give you the period. And you expect, like by understanding this period map in 3 dimensions, you might expect to have some kind of special geometry. This is indeed true. But this is very subtle. For simplicity, let me consider a case without like mass parameters, and this space has a natural symplectic structure, like this is perfectly paired, which is with the dual version of the intersection pairing. Now, here's the basic question, and if you believe this construction, this low energy effective theory of Coulomb branch described by this CyberWitten geometry, but what is the CyberWitten differential associated to singularities? The naive guess is the following: like if you start, so you need a straight form anyway if you want to integrate of the straight form over like 3-dimensional vanishing cycles, and somehow the naive guess is like, oh, let's pick up this standard volume form that appears in many places in the physics literature, and then you look at the step, you guess like the CyberWitten differential is a family of straight forms of the following type, like it's a volume form over this one form. This is deformation of this deformation of the polynomial. And if you compute the periods of this guy, you might expect to find some kind of special geometry. This is actually indeed true. If you find the n equals 2 pre-potential by understanding this period, if you're working with like 80 singularities, it's like a central charge less than 1. And then you started to do some calculations beyond 80, you started to find something wrong happening. And you might be wondering, like, what's happening? This phenomena appeared also in 2D case, like when people studied like find the flat coordinates and the solutions of WD-Weber equation. You want to find the period maps from logarithmic models from these oscillating integrals. You might compute the period for some kind of trivial volume form. In the ADE case, you really find the potential functions, and you find the correct flat coordinate. But if you go beyond ADE, you get something wrong again. And there you have to replace the volume form by the primitive form, just as I mentioned. And this appeared again in the story. So this is our solution. I mean, it's joint work with Danxi and Yao early in this year. We find the following, like for threefold singularity, if you want to get CyberWitten differential, you need to put this one by this Qt-Cyto's primitive form. And the reason for this one is the following, like somehow you want the existence of the n equals 2 pre-potential. And then the main support is like you need whatever you do, like to understand this period map, you need this kind of integrability condition for the existence of the pre-potential. And somehow this is not true for any kind of period map. If you put an arbitrary one, this doesn't hold. So basically, the verification of this integrability requires a connection between the intersection pairing for valential homology and the period map. Now, this primitive form arising from semi-infinite Hodge structure precisely gives such a connection. And if you explore that one, you find this is true for primitive period map. And that's our solution. So let me comment a little bit about this curved CyberWitten case and the threefold case. And this construction also generalizes into curved case. I mean, you find like if in the curved case, if you start with a primitive form, then the CyberWitten differential is given by the first descendant of the primitive form over this df. And if you want to compute the correct CyberWitten stuff, you have to use the primitive form over this guy. And now you see like this one picks up the first descendant. This is like a T operation I mentioned. The previous page, like this threefold case is like just a primitive form. And there's some deep reason for the shift. I mean, well, this is by the Hodge theory, but somehow you can imagine like if you go to some other dimensions, you try to explore what's happening. You can geometric engineering like some kind of like 5D hypersurface singularity example, and you find the -1 descendant of the primitive form, and give rise to this kind of CyberWitten differential. This is a very universal. I mean, this construction. So let me give, in the rest of the time, let me give you some examples of the primitive form that give rise to this kind of CyberWitten solution to get you some feeling about this. As I mentioned, like this primitive form arises from this semi-infinite Hodge structure, but so the construction is rather involved, but in some examples we know what it looks like. So for example, consider this case. This model, like assume like this condition holds. So this singularity is basically ADE type. And again, this example can be reduced to curved case because you see these two terms, like Morse type. You can reduce this. You can basically eliminate these two variables, so become a curved singularity. But anyway, we know like in the ADE case, this primitive form is rather trivial. It's not that trivial, but it's simple. This primitive form is given by the trivial volume form. It doesn't depend on the choice. It doesn't depend on the deformation. But take any kind of unfolding you like. You take this trivial form. You compute the period of this guy over the valence cycles. You find this CyberWitten case. So this is why, I mean, usually we'll do examples like in ADE. You use this as to explore what you find, and you find the correct answer. But now, if you go to anything beyond ADE, you find something wrong. So, for example, let's look at this case. This is like one example of like a simple elliptic example. This example cannot be reduced to curved case, so you see like this is like a 3-3. And if you look at the universal deformation of this example, this one has 8 deformations, lambda 1 to lambda 8. And this one deformation, which is very essential, So the previous 7 deformations are somehow relevant. This one is irrelevant. Now, in this case, the primitive form, this one is marginal, by the way. So this example, primitive form is non-trivial. So comparing to the previous case, like ADE case, if you do this period map over a vanishing cycle, you find the Seiberg-Witten case. But in this case, if you just naively do the period map for this trivial form, you get something wrong. But I have to divide this trivial form by some functions, some periods on the corresponding cubic elliptic curve. This is defined by this marginal deformation. And then this is actually the primitive form in this example. This is only unique. You pick up any period, this works. And you see like this example shows like this form that you have to insert to describe Seiberg-Witten solution is really non-trivial. I mean, depends on the choice of this parameter. Finally, like this is another more general example. Like this is a case like when central charge is bigger than 1. So there's highly non-trivial parent mixing between these relevant and irrelevant deformations. And actually, so far, we don't know a closed formula for the primitive form in general for this case. But we have some algorithm to compute what it looks like asymptotically. So here I give you one example. This is like a type E12 of the unimodular exceptional singularity. So again, because of these 2 terms, this example can be reduced to the curve case. And this mean universal deformation is described by like this part. They have 12 deformations. And this one is special, it's irrelevant deformation. Now, with this one, you can compute, try to look at what is Seiberg-Witten differential look like. As I mentioned, like there's no closed formula, but a couple of years ago, like with Chanton-Li and Kyoji Saito, we found a recursive formula to compute the asymptotic summation. And for example, if you apply this algorithm to compute this case, you find like this primitive form look like complicated. So there's a highly non-trivial mixing between this like relevant and irrelevant deformations. All terms appeared. And so far, we don't have a good understanding of these terms, but we know this exists. And in particular, comparing to the previous case, this is like a marginal case. The form is divided by the periods. That's the usual, also the standard structure appeared in physics. This case is not like it's not a rescaling of the trivial form and depends on deformation in a highly non-trivial way. And so far, we don't have a very good understanding, like a physically or mathematically understanding of the structure. But again, I'd like to mention like this structure arises from just understanding basically what's the Hodge structure for this holomorph function. Okay, that's all I want to say. Thank you very much. Thank you.